Okay, I have here a new example. So in this problem, we are asked to formulate a shear and moment equation. And using this equation, we have to determine the shear and moment at 5 meters from A. So we have here an overhang beam. We have a 150 kilonewton that is acting at point A. We have 20 kilonewton per meter that is acting 5 meters from B to C. And we have 50 kilonewton per meter uniform load that is from C to D, that is 5 meter length. Now, the first thing we do here is, of course, to determine the reactions at B and D. Now, we have the reaction at B here, that is, we know this is a hinged, so we should have two reactions. However, since upon seeing the beam, we do not have horizontal load, so we can say that our horizontal reaction at point B is equal to 0. So we only have one reaction at B, that is the vertical, that is, let's say that's RB. And at point D here, we have the vertical reaction since this is ruler, so we have RD. Okay? So we can now compute for the reaction B and D by summing up moment and forces. So we can sum up moment from D. So let's try to find first the reaction at B. So by summing up moment at point D, so we have summation of moment at D is equal to 0. When we have our moment that is counterclockwise, then we assume that as positive. So we have first our RB, and our RB that is negative since the rotation of RB with respect to D is clockwise. So we have negative RB, and the moment arm is 10 meters. That is the distance from RD. We have 5 plus 5. Now, for the concentrated load, 150 kilonewton, since the rotation is 150 kilonewton, is counterclockwise with respect to D. So, therefore, we have here plus 150 times the moment arm from D, that is 5 plus 5 plus 2.5. Then we have 12.5. And then we have the moment of the uniformly distributed load, and we know that this uniform distributed load 20 kilonewton per meter is represented by a resultant force, okay, and the resultant force here, that is 20 kilonewton per meter times the length of action, and we know that's 5 meters, so we have our resultant force that is 20 times 5, and then we compute the moment arm. Since we know that the resultant acts midway, or acts at the midspan of the length of action. And we know, since the length of action here is 5, so therefore our resultant acts 2.5 meter, or that is the 1/2 of 5. And this is 2.5 meters from our B. However, our moment arm, again, that is relative to D. So we have our distance from D here, that is 10. We have 5 plus 5 minus 2.5. Then we could get 7.5 meters. That is the location from D. So we have 7.5 meters. And then we have the resultant of uniform load 50 kilonewton per meter. This gives us 50, the uniform load, times the length of action, that is 5. Okay? And then this gives us 200, okay, 250 kilonewton. So we have here, and since the rotation of 50 kilonewton per meter is counterclockwise, we have plus, that is 50 times 5, and then the moment arm from D is the 1/2 of 5 meters, that is 2.5. So we have here times 2.5 and is equal to 0. So we have our reaction at B, that is equal to 325 kilonewton. So this one is 325 kilonewton. Now we can compute the reaction at D by summation of forces vertical and all the force acting upward are positive. Okay, so we have the RB, that's positive, plus the reaction at D, minus 150 kilonewton, that is the concentrated load, minus the resultant of the uniform load 20 kilonewton per meter, that is 20 times 5, minus the resultant of the uniform load 50 kilonewton per meter, that is 50 times 5, this equals to 0. And since we have computed already the value of RB, so we have 325 as RB. So we copy everything. So we have our RD here that is equal to 175 kilonewton. So we have now computed the reactions. Now, we can now proceed to the shear and moment equation. But first, we need to decide on which we are going to have our cut section. Now, in this case, we know that our segment A to B is continuous in the sense that our load here, or our concentrated load, is acting at point A. So therefore, within A to B, we do not have a load. Okay? So therefore, our moment equation and the shear equation at this point is equal, or are the same. So we have, this could be our cut section 1. And our cut section 1 is, let's set our point here as our reference point. So we have X distance from the A. Now, we could also have another cut section here by looking at B to C. And we know that member B to C is continuous since we only have one single uniform load here that is 20 kilonewton per meter. Okay, so therefore our equation all throughout from B to C is equal or is the same. Okay, but in the case that we do have a concentrated load here, again, the concentrated load causes discontinuity of our segment BC. So in that case, we need to cut this point and cut this point since they have different shear and moment equation. But again, we do not have a uniform load at this interval B to C, then we could set them as our second cut section. Okay, let this be our section 2. And now we have segment CD, and our CD here is continuous since again we have only one uniform load that is 50 kilonewton per meter, and we do not have concentrated load here. And then we only have one single load here is 50 kilonewton per meter. So therefore, our moment equation and shear equation between this interval is equal. So we could have our cut section 3 here at this segment. Okay. Again, all our cut section should be located X distance from our A. So we should have the same point of reference, and that is A. So the same as our cut section 3. So we have X distance from A. In cutting a section, we should consider the continuity behavior of our beam. There are a change in load, okay? Or there is an additional load, so you need to cut that separately. So now let's try to isolate first or compute the internal moment and internal shear at section 1. Now, if we cut our section at this point, we could have our internal shear and internal moment exposed. So we have an internal shear that is acting downward. So let's assume that's positive, since we know that if we have our internal shear acting downward on the right face of our beam, that is considered as positive. That is in our sign convention. And then our moment also here, let's assume that as our is positive. It is positive since it generates a smiling curvature. Now, if we have our bending moment like this one, correct? So therefore, if we cut our beam here at section 1, we only have 150 kilonewton load to be included in the cut section. So this is our cut section 1, and our cut section 1 here is valid from the interval 0 to 2.5. Since again, our cut section 1 here is continuous from A to B, and with our reference here is from A, so therefore we have our value of X from 0 to 2.5, since we have 2.5 meter distance from A to B. So that is the interval. That's the interval of our shear and moment equation. So we can only use the moment equation and the shear equation within this range. Now in section 1, we have our 150 kilonewton that is included, and we have the internal shear that is acting downward at internal moment, and our section 1 here has an X distance from our point A. So this is again, this is point A. Okay, So we have here the summation of forces vertical. So let's first compute for the shear equation. So we sum up force vertical, and all the force acting upward are positive. Then we have negative 150 kilonewton minus the internal shear 1 is equal to 0. So we have our internal shear that is equal to negative 150. Okay, and this is in kilonewton. Since again, we have an equation here that does not include variable x, since we know that at this point, we do not have a load. Okay, we do not have force. So therefore, we have a 0-degree shear diagram between A and B. Okay, since we do not have a variable x. So we can now compute for the moment equation. So this again, this is our shear equation. Now for the moment equation, we sum up moment at section 1. Let's say that's 0. Counterclockwise are positive. Then we have 150. Again, the rotation of 150 is counterclockwise, so that's positive. Then the moment arm x plus our moment, internal moment 1 at section 1. So we have m1, that's positive, is equal to 0. So we have our moment equation at section 1 is equal to 150x, and this is a negative since we transposed it to the right side of the equation. And this is our moment equation at section 1. Okay, and this one is the shear equation at section 1. So we are done with section 1. So let's now try to isolate section 2. Now in section 2, this one, if we isolate this, we could have our 150 kilonewton included and portion of 20 kilonewton per meter also included in our cut section, and as well as our support RB will also be included. So and then we have our section 2 here that is isolated from the entire beam, and we have our 150 kilonewton that is included in our cut section, and we have the uniform load, the portion of the uniform load that is also included. Then we have 20 kilonewton per meter. It's the cut section, and our x here, we set that as our reference, that is from A, okay, and to our cut section 2. We also have our reaction RB 325 kilonewton that is also included in the section, cut section. Now since our A to B here has a distance of x, and we know that A to B is 2.5 meters apart, and then so therefore our length of action of the uniform load is x minus 2.5. So we have x minus this length here, so the remaining would be x minus 2.5. So we can now compute the shear and moment equation. So let's start with the shear equation. Then we can sum up forces vertical is equal to 0. All the force upwards are positive. So we have the reaction RB that is 325. Okay. Then we have the concentrated load that is 150 kilonewton minus the uniform load. Now our uniform load here is represented by a resultant force, and the magnitude of this resultant is 20 kilonewton per meter times the length of action that is x minus 2.5. So we have here therefore that is the magnitude that is 20 times x minus 2.5. Okay, then we have the internal shear exposed in the cut section. Then that is we have minus the internal shear acting downward, that is internal shear 2, and this is equal to 0. So our shear equation here is equal to, and this gives us 175. Okay, since 325 minus 150, and then we have minus 20 times x minus 2.5. Okay, so we transpose shear 2 to the right side, so we could have positive, but I rewrite it this way. So we have shear 2 here, that's equal to, and the sign of this one remain, so we have minus 20 times x minus 2.5. So this is our shear equation number 2 of section 2. Now let's compute for our moment equation for this one. Okay, let's say at 2 is equal to 0, the counterclockwise are positive. Then we have here the reaction 325. Now the moment arm, or the distance of the reaction from our cut section 2, that is x minus 2.5, correct? That is the horizontal distance. And this is negative since it rotates clockwise. Now we have 150 kilonewton here that is rotating counterclockwise, so that is positive 150 times the moment arm from section 2, that is x, the distance from section 2. So you have x here. Then the resultant of the uniform load, that is, we have, let's see, that's positive 20 times x minus 2.5. Then the moment arm. Now we know again that our resultant is acting halfway, okay, or acting at the mid span of its length of action. So therefore, our length in that case is equal to the half of x minus 2.5. Okay, that's the distance from section 2. So therefore, we have here times x minus 2.5 over 2. This is the moment arm. Then we have the internal moment that is counterclockwise. So we have plus the internal moment 2 is equal to 0. So we have now our moment equation. We further simplify this one. That is equal to, let's transpose everything to the right side. That is, we have 325 times x minus 2.5. Then we have 150x here. That is negative 150x. Now we could cancel out 20 by 2. So we could simplify it by 20 divided by 2. Then we have 10. But since we transpose this term to the right side, then we have negative 10. Then we can combine x minus 2.5. So we could say that's x minus 2.5 squared. Okay, so this is now our moment equation 2. And now this equation, this shear equation and the moment equation is valid only in the beam from B to C. So therefore, our section 2 here is valid for when our x here is 2.5, okay, up to C, that is 7.5. Okay, so when we look at the figure again, so our section 2 here, when our reference point here is from A, so our x here is always reference from A, so therefore our section 2 is from B to C. Since our segment is continuous from B to C, we only have 20 kilonewton per meter as load in that range. So we do not have a change in loads. Hence, it is known to be as continuous. So our x here is from 2.5 from A, and then we have 7.5 from A. And now we are done with section 2. So now let's compute the shear and moment equation at section 3. So our section 3 here is valid from C to D. Since our segment is continuous from C to D, we have only 50 kilonewton per meter load at that point. So our x here is from, that is 7.5 from A to 12.5 meters from A. Okay? Now, by cutting at section 3, we have our 150 kilonewton concentrated load included. We could also have the entire 20 kilonewton per meter load is included as well. And we have the reaction is also included, and portion of 50 kilonewton per meter is included. Okay? Since we cut in between this load, 50 kilonewton per meter. And then we have here our section 3, okay? That is, we have 150 kilonewton, 20 kilonewton per meter, and 50 kilonewton per meter. Okay? And then we have our section 2 here, that is x distance from A. Okay? And then, if we cut this at section 2, we could have our internal shear exposed. Let's say that internal shear 3 and the moment 3 is also exposed. And then the section 3 has an x distance from A. Now, this interval again is valid only for x, that is when we have 7.5 meters up to the end of our beam, that is 12.5 meters. So we have only at point C to point D. So we could sum up force is vertical is equal to 0, force acting upward positive. Then we could have the reaction RB, that is 325, acting upward, that's positive. Then minus the concentrated load 150 minus the resultant force of 20 kN per meter uniform load, this one, and that gives us 20 kN per meter times the length of action, that is 5. Okay, then minus the uniform load 50, then the length of action, since we know that from A to section 3 we have x, so therefore the length here is x minus 7.5. So we add 5 plus 2.5, then we deduct it from x, so we have x minus 7.5. This x minus 7.5. So that is the concentrated load. And then we have the internal shear here, that is V3 acting downwards. We have the internal shear 3, and this equals to 0. So we have our shear equation 3, that is equal to, so if we combined all these constant, we could have 75 minus the remaining would be 50 times x minus 7.5. Okay, and this is our shear equation. So we can now compute for the moment, that is we have summation of moment at A, all at section 3 rather, it's equal to 0, counterclockwise positive. Then we have the reaction, that is 325 times the moment arm. Okay, so we have to determine this distance from our section 3. Now we know, since this is x and the distance from A to B is 2.5, then our distance here is x minus 2.5, correct? So we have here x minus 2.5. Then again, this is reaction here, there is clockwise rotation, so we have set as negative, then plus 150 times the moment arm x plus the resultant of 20 kN per meter, that is 20 times 5. Okay? However, the location of the resultant from 3 is unknown yet. So how are we going to determine the location of our resultant from section 3? This one here. So that is just, since we know that this one here is 2.5 from B, okay, and that is from A, that is 5 meters from A. So the resultant here is located 5 meters from A. Okay, since 1/2 of 5, that is 2.5, plus 2.5, which is the distance from B to A, then we could have 5 meters. So therefore, the distance from 3 to the resultant is x minus 5, correct? So that is x minus 5. And then we have the resultant of 50 kN per meter, that is plus 50 times the length of action, that is x minus 7.5. Then the location of our resultant from 3, that is 1/2 of x minus 7.5. So we have x minus 7.5 over 2. And then we have the internal moment, that is counterclockwise. So plus moment 3 is equal to 0. So we have our moment equation 3 here, that is equal to 325 x minus 2.5. Okay, we transpose that at the right side, minus 150x minus 20 times 5, we have 100 x minus 5, 50 divided by 2, that is 25. Then we combine x minus 7.5, thus we have raised to the 2, and this should be in negative since we transpose that to the right side of the equation. And this one now is our moment equation of 3. You can further simplify this moment equation here, but this will do for me. Okay, so I have here the shear and moment equations tabulated. Okay, so we have from A to B, that is from 0 to 2.5. We have 2.5 to 7.5, that is segment B to C, and we have 7.5 to 12.5, that is segment C to D. So we will be using the shear and moment equations to plot our moment and shear diagram. Okay, so let's start with our shear diagram. Okay, this one here. Now, let's start from the leftmost side, that is at point A. And we know that at point A, we have our x is equal to 0. And in between A to B, we have our shear equation, that is this one. And that is, we have at x equal to 0, our shear diagram or shear equation, that is equal to negative 150. So at x equal to 0, since we do not have variable here and our x here is raised to 0 degree, okay, if we have x raised to 0, then we have 1, correct? So therefore, our x would be eliminated. So our shear diagram or shear point at x equal to 0 or at point A is equal to negative 150. So we plot that at the below the reference line. This is the reference line 0. So we have negative 150 below this one. Okay, so we will not try to draw our diagram into scale due to space constraint. Now at x equal to 2.5, this is at point B, we will still be using this equation. And then we have our V here is also equal to negative 150. So if we don't have load diagram, so we will start in our diagram or in shear diagram as 0 degree order. So we will plot it by connecting these two, that is a perfect horizontal. So we have here that is negative 150. Okay, now let's draw the shear diagram in segment BC at x here is equal to 2.5. Okay, so we will start at B for segment BC, and we are going to use the equation B to C, that is this equation here, this one. V is equal to 175 minus 20 times x minus 2.5, and we set x here that is equal to 2.5. So our shear point here is equal to 175 kilonewton. So if we plot that in our diagram, they would have positive 175. So we go above our reference line. So we will plot our diagram at this point. Okay, so let's say this is 175. Okay, so let's not include the unit. So at point C, we have x here that is equal to 7.5. That is the distance from the A. Okay, this at point C. Now we will still be using this equation. Okay, that is 175 minus 20x minus 2.5. Then we would have 175 minus 20. Then our x here is 7.5 minus 2.5. This will give us 75 kilonewton. So therefore, we go below the 175. So we plot here. This is 75. Okay. Then since our load diagram is in 0 degree, our shear diagram here should be in the first degree order. So we have to connect these two here, and that is now our shear diagram for BC. Okay, now let's proceed to segment CD. That is, we have at x is equal to, let's start with x equal to 7.5. This is at point C. We have our shear at that point, or we will be using the shear equation C to D. This equation here, that is 75 minus 50 times x minus 7.5. And we set here as our x is 7.5. So we could have a value of 75 kilonewton. Since we have 75 kilonewton and it is the same with our previous computation, so we will not be moving our point. So our point will remain at this location. Okay, so let's now proceed to the at point D, and we set that x equal to 12.5. That is at point D. We have our shear point, that is using again this equation, that is 75 minus 50 times 12.5 minus 7.5. This equals to negative 175 kilonewton. So therefore, our diagram will be below our reference line. Okay, our 0 reference point. So we have here, let's say at this point, that is negative 175. Again, since we have a 0 degree load, so therefore we have first degree diagram. Then we connect this diagram, so we could have a shear diagram. Okay, so this point. So we are done with our shear diagram. Now let's move to moment diagram. Now let's start at the leftmost of our equation. So at point A, again, we still have x equal to 0, but we have to use this moment equation that is negative 150x. X equals to 0, so it is at point A. So we will be using the equation moment is equal to negative 150x. And we know that x equal to 0, so therefore we would have a value of 0 kilonewton meter. Okay, so at point A, we have, at this point, this is 0. This is correct since we do not have support here. It is free end, so our moment at that point is 0. Now, at x equals to 2.5, or that is at point B, using this equation, okay, again, that is moment is equal to, that is, we have negative 150 times 2.5 is equal to negative 375, and the unit is in kilonewton meter. So we have our moment point at point A, when our x equals to 2.5, that is at point B, that is negative 375 kilonewton meter. So let's try to plot that in our diagram. So at point B, we have negative 375. So let's say at this point, okay, we have negative 375. Okay. However, take note, our shear diagram is in 0 degree, so therefore our moment diagram should be in the first degree. So it is a line or an inclined line with a constant slope. So therefore, if we try to draw that one, so we could have this moment diagram from 0 to negative 375. Now for segment BC, we will be using this equation that is 325, okay, that times x minus 2.5 minus 150x minus 10 times x minus 2.5 squared. We have at x is equal to 2.5, and that is at point B, using the equation moment is equal to 325 times x minus 2.5 minus 150x minus 10 times x minus 2.5 squared. Okay, by substituting the value of x, that is 2.5, then we could get the answer equals to negative 375 kilonewton meter. Now, when drawing moment diagram, you can check whether your moment is correct or your equation is correct if it has the same answer from the previous equation at the same location. So take note, we have at point B, using different equation, we have negative 375, and we have at point B, using this equation, we still have negative 375 kilonewton meters. So therefore, we have correct moment diagram or correct value of internal moment. So therefore, since that is negative 375, so we will not be moving our point. So we still at this point. Okay. Now at point C, we have x equals to 7.5. This is at point C. We have the same moment equation, but our x there is 7.5. Then we could get the answer, and our answer here is equal to 250. That is in kilonewton meter. That is positive, so then we have to plot that above our reference line. So therefore, at point C, okay, so we have 250 positive, so we can plot this at this point. So let this point be 250 kilonewton. That's positive. Now, our curvature here, take note, since our shear diagram is decreasing and it is in the first order, so therefore our moment diagram is in frowning curvature and it should be in the second order. Again, if we have decreasing shear diagram, then therefore our moment diagram is frowning. Okay? And if we have increasing shear diagram, then we should have a smiling moment diagram. Now, after 250 kilonewton meter, we will not go directly at point D. Since take note, we have still positive internal shear at this point. Okay? So instead of going directly downward, going this negative shear here, or referring to the negative shear, we will still need to go upward since again we have a positive internal shear. So how are we going to compute the moment at this point? Okay? So if we have this point, so that is zero shear, again, this point is, we have our shear is equal to 0. So to compute for the moment at that point, we need to compute first the location of our internal shear wherein it is 0. So again, we need to compute for our x, but our x, again, when we compute for the equation, our x, the reference line is from the A. And that is, we have compute for the x wherein our shear is equal to 0. So what is the equation that we will be using at this case, in this case? Now take note, our internal shear is within C to D. So therefore, we need to use the shear equation, okay, for C to D, and this equation is this one. We have 75 minus 50 times x minus 7.5. Now, how are we going to compute for the x? So we set at this point when shear is equal to 0, so we will be computing for our x. So we have the equation 75 minus 50 times x minus 7.5, and then our shear is equal to 0. Okay, so we need to compute for our x here, and our x is equal to 9 meters. So therefore, the location of our shear equals to 0 is 9 meters from A. So we have here 9 meters. Now, using the value of x here, that is 9 meters, we can now compute the moment at this point. So we need to use the moment equation, okay? And the moment equation that we will be using is the moment equation of section 3. This one, this longer equation here. But let's compute first the moment at point C by using this equation. So we have x is equal to 7.5, that is at point C. We have the equation is equal to 325 times x minus 2.5 minus 150x minus 100 times x minus 5 minus 25 times x minus 7.5 squared. So we set the value of x here is equal to 7.5, then we could have 250 kilonewton meters. So the same as with the previous equation at the same location, point C. Now let's compute the, so therefore our point here is correct, so our moment at this point is correct. So our goal here again is to compute for our moment at this point. So we set x here is equals to 9 meters. So we have, what is the moment when our x is equal to 9 meters? So we have the moment equation. Using this moment equation here, then we could have m is equal to, okay, let's use this equation. That is equals to 306.25 kilonewton meter. Okay? So therefore, at this point, 9 meters from A, our moment is 306.25. So we plot at this point. Okay? So let's not take the scale seriously since we have limited space now for shear diagram and moment diagram. So we have, and this is 306.25. Now take note, our shear here is in first degree, so therefore our moment is in second degree. And then it is decreasing, so therefore we have a frowning curvature. So the same as with this one, we have decreasing shear diagram, so therefore we should have frowning moment diagram curvature. Okay? Now, we can now go to point D. So let's compute our point D. We have at x is equal to, at point D we have 12.5 meters from A. So using this equation again, so since we are still in the segment CD, so we have still the same equation. That is, we have 0 kilonewton meter. So therefore, our moment at this point is 0. And since again, we have decreasing shear diagram as what you can see here. So it is decreasing, and in and it is in the first degree. So therefore, our moment diagram should be in the second degree order and in frowning curvature. So we should have this curvature here. So this is now our shear and moment diagram. Now for the second question, we are asked to determine the shear and moment in which that is 5 meters from A. Okay, and we know that if this is 2.5, so therefore from B we have 2.5, and that is the midspan between B and C. So we are asked to compute the moment at this point. So we need to use the shear and moment equation of our segment BC. So we will be using this equation here, that is the 175 minus 20x minus 2.5 for shear, and for moment this one. X is equal to 5, okay? So we are determining shear, internal shear, and the internal moment. So we have the shear equation at B to C, that is equal to 175 minus 20 times x minus 2.5. So we set x is equal to 5. So therefore, we could have the value of 125 kilonewton. And for the moment, we have the moment equation, that is 325 times x minus 2.5 minus 150x minus 10 times x minus 2.5 squared. So we set x is equal to 5. So we have our moment, that is equal to 0 kilonewton meter. So therefore, at x equal to 5, we don't have moment. So therefore, we could say that the shear at this point, which is 5 meter from A, is 125 kilonewton. And the moment at this point, which is also 5 meter from A, is 0 kilonewton meter, which means that we do not have moment at this point. So I know that moment equation is very long, but I have the easiest method, which is shear and moment diagram using area method, which will be discussed to you in the videos to come. So I have additional example in my next video. So I have posted the link of the part 3 of this discussion in the